It begins without warning. Somewhere in the universe, a region of space that had been quiet for billions of years suddenly releases more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime. Space itself becomes saturated with radiation. Detectors orbiting Earth register a spike so intense that, for an instant, the gamma-ray sky is dominated by a single point. This is a gamma-ray burst. The name sounds almost casual, but the physical reality is anything but. A gamma-ray burst is not an explosion in the everyday sense. There is no expanding fireball like a bomb, no steadily growing shockwave that sweeps outward in all directions. Instead, it is a focused, relativistic discharge of energy, confined to narrow jets and compressed into timescales that push the limits of causality. Some bursts last less than 1/10 of a second. Others continue for minutes. In that brief window, they become the brightest electromagnetic events ever observed. The photons arriving at our instruments are not ordinary light. Gamma rays sit at the extreme end of the electromagnetic spectrum, with energies measured in thousands to millions of electron volts. A typical visible light photon carries just a few electron volts of energy. A gamma-ray burst photon can carry 1,000,000 times more. These are not gentle waves. They are the most energetic messengers light can produce without becoming something else entirely. When a burst goes off, the detectors do not see a smooth rise and fall. They see chaos. Spikes and dips unfold on millisecond timescales. The brightness can double or collapse in less time than it takes a neuron to fire. That variability alone tells us something profound. Whatever is producing this radiation must be extraordinarily compact. Light cannot vary faster than the size of its source allows. If brightness changes in a millisecond, the emitting region cannot be larger than about 300 kilometers, roughly 186 miles. That is smaller than many cities, yet the energy output rivals or exceeds that of entire galaxies. This combination, immense power and microscopic timescale, is the defining signature of gamma-ray bursts. It is also what makes them so difficult to explain. At peak intensity, a gamma-ray burst can briefly outshine every star in the observable universe combined if you compare raw luminosity. That statement comes with an important caveat, one that astronomers learned only after decades of confusion. The emission is not isotropic. The energy is not radiated evenly in all directions. Instead, it is tightly collimated into narrow beams, like cosmic searchlights sweeping across the universe. We see a burst only if one of those beams happens to intersect Earth. Even accounting for that beaming, the numbers remain staggering. The isotropic equivalent energy, the energy the burst would have if it radiated in all directions, can exceed 10 to the 54 ergs. Converted into more familiar terms, that is roughly equivalent to converting the mass of the Sun directly into energy, multiple times over, in a matter of seconds. Physics allows such numbers only under extreme conditions, where gravity, relativity, and quantum processes are all operating at full intensity. The dominance of a gamma-ray burst is not subtle. During those seconds, it becomes the single most important thing happening in the electromagnetic universe. Gamma-ray detectors see the background sky vanish beneath it. Other sources, pulsars, active galaxies, even solar flares, fade into insignificance. If human eyes were sensitive to gamma rays, the night sky would briefly be reduced to one blinding point, brighter than everything else combined, then disappear as abruptly as it arrived. Yet nothing in the visible sky changes. No star flares, no new point appears. Gamma rays pass straight through Earth's atmosphere without ever reaching the ground. They announce themselves only to machines in orbit, silently, impersonally, leaving behind digital traces that scientists must later reconstruct into a physical story. The brevity of these events is part of what makes them so unsettling. Some bursts are over before instruments can fully reconfigure. A detector triggers, records a few hundred milliseconds of data, and then the universe returns to normal. The source may never emit gamma rays again. There is no warning, no build-up, and often no repetition. These are one-time events, signatures of catastrophic transformations rather than ongoing processes. At their shortest, gamma-ray bursts last just a few milliseconds. That is comparable to the time it takes light to cross a small planet. At their longest, they may persist for several minutes, sometimes with extended emission that fades gradually rather than cutting off cleanly. In either case, the time scale alone rules out most astrophysical mechanisms. Stars do not change that fast. Galaxies certainly do not. Even supernovae unfold over days to months. Gamma-ray bursts operate in a regime where only the most compact objects, neutron stars and black holes, can respond quickly enough. The energies involved also impose strict constraints. Producing gamma rays at these intensities requires particles to be accelerated to extreme velocities, often within fractions of a percent of the speed of light. Magnetic fields must be colossal. Matter must be organized and expelled in ways that prevent the radiation from immediately being reabsorbed or scattered away. Ordinary stellar processes fail immediately when confronted with these requirements. One of the most counterintuitive aspects of gamma-ray bursts is how concentrated they are in time. If the same total energy was spread out over years instead of seconds, the event would be unremarkable on cosmic scales, but by compressing it into such a narrow temporal window, nature produces an intensity that is almost absurd. Power, after all, is energy divided by time. Gamma-ray bursts are not just energetic, they are violent in the truest physical sense. This intensity has consequences. Inside the burst region, radiation pressure dominates everything else. Photons carry momentum, and at these energies, that momentum can rival or exceed the mechanical pressure of matter. Any stray particle caught in the outflow is accelerated to relativistic speeds. The environment becomes opaque to its own radiation unless conditions are just right. To escape, the gamma rays must be produced in regions where the density has already dropped, where the outflow has expanded and thinned enough to let light stream freely. This requirement leads to one of the core puzzles that will echo throughout this episode. How do you produce gamma rays without trapping them? If the source is too dense, photons scatter endlessly and lose energy. If it is too diffuse, there is nothing to generate the radiation in the first place. Gamma-ray bursts exist in a narrow corridor of physical possibility, balanced between opacity and emptiness. From Earth's perspective, these bursts appear randomly across the sky. There is no preference for the plane of the Milky Way, no clustering around known stellar populations. That isotropic distribution was one of the earliest clues that gamma-ray bursts are not local phenomena. They are not confined to our galaxy. They originate across the observable universe, at distances measured in billions of light-years. The light arriving at our detectors today began its journey when Earth itself was young, or had not yet formed at all. Because gamma rays travel at the speed of light and interact weakly with intervening matter, they preserve a pristine record of their origin. They are not scattered by dust. They are not absorbed by gas clouds in the same way visible light is. When we detect a gamma-ray burst, we are seeing a direct imprint of an event that occurred deep in cosmic history, largely unaltered by the space it crossed to reach us. There is a strange duality to this. On one hand, gamma-ray bursts are unimaginably distant and untouchable. On the other, they are intimate in their precision. Millisecond timing structures encode information about magnetic fields, shock fronts, and particle distributions in regions smaller than Earth. Few astronomical phenomena allow such direct inference about processes occurring at such extreme energies and compact scales. Despite their brightness, gamma-ray bursts pose no threat to life on Earth in their observed form. The distances involved ensure that even the most powerful bursts deliver only a faint trickle of energy by the time they arrive here. But in principle, a sufficiently close burst, properly aligned, could have severe biological consequences. That possibility is not science fiction. It follows directly from the same physics that makes these events so luminous. The universe contains engines capable of delivering lethal radiation across vast distances, even if the odds of being in the line of fire are extremely small. What makes gamma-ray bursts briefly dominate the observable universe is not just their raw output, but their contrast. The gamma-ray sky is normally quiet, outside of solar flares and persistent sources like pulsars and active galactic nuclei. The background is low and stable. When a burst appears, it towers above that background by orders of magnitude. For a few seconds, the universe announces that something extraordinary has happened, and then falls silent again. Before we go deeper, if you enjoy exploring the quiet wonders of the cosmos like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow, and it keeps these journeys alive. The dominance of a gamma-ray burst is fleeting, but its implications linger. Each detection raises questions about origin, mechanism, and consequence. What kind of system can channel such energy into such a narrow beam? How does matter behave when pushed to these extremes? And why do these events occur at all, scattered across cosmic history like brief, violent punctuation marks? To understand that, we have to step back, not in space, but in time, to the moment humans first noticed that the universe was capable of producing flashes this intense, without any warning, and without any obvious source in the sky. The first gamma-ray bursts were never meant to be found. In the early 1960s, the sky was being watched for an entirely different reason. The United States and the Soviet Union had just signed the Limited Test Ban Treaty, which prohibited nuclear weapons tests in the atmosphere, underwater, and in space. Enforcing that treaty required a new kind of vigilance. Nuclear detonations produce a distinctive flash of gamma radiation, followed by characteristic signatures that can be detected far from the explosion site. To make sure no one was cheating, the United States launched a series of satellites whose sole purpose was to listen for those flashes. These were the Vela satellites. Beginning in 1963, pairs of Vela spacecraft were placed into high-altitude orbits around Earth. Their instruments were simple by modern standards, but exquisitely sensitive to gamma rays. They were designed to discriminate between nuclear explosions near Earth, cosmic rays, and background radiation from the Sun. The expectation was straightforward. If a forbidden test occurred anywhere in space, Vela would see it. For several years, that expectation held. The satellites performed quietly, reliably, and uneventfully. Then, on July 2nd, 1967, something strange appeared in the data. The detectors recorded a burst of gamma rays unlike anything associated with a nuclear detonation. The timing was wrong. The energy distribution was wrong. The signal arrived almost simultaneously at multiple satellites, but not in the pattern expected for an explosion near Earth or the Moon. It did not resemble solar activity, and it did not repeat. At first, the event was treated as an anomaly. Instrument glitches were common in early space missions. Cosmic rays could occasionally mimic gamma signals. But then it happened again and again. Over the next few years, the Vela satellites detected several dozen similar flashes, each brief, intense, and inexplicable. What made these signals particularly unsettling was what they were not. Nuclear explosions have a very specific gamma-ray signature, an initial prompt flash followed by a slower decay from radioactive debris. The Vela events lacked that structure. They were sharp, irregular, and often complex, with multiple peaks. No known weapon could produce such a profile. More importantly, the timing between satellites indicated that the sources were far beyond the Earth-Moon system. By comparing the arrival times of gamma rays at different spacecraft, scientists could triangulate the direction of each burst. The geometry ruled out terrestrial origins. These events were coming from deep space. That realization triggered a problem. If these flashes were not nuclear tests and not solar flares, then they were something entirely unknown. But the data were classified. The Vela program was a military asset, and its observations were protected accordingly. For several years, only a small group of scientists with security clearance were even aware that the signals existed. Among them was Ray Kleber-Zadell, a physicist working at Los Alamos National Laboratory. Along with colleagues Ian Strong and Roy Olson, he began a careful analysis of the mysterious bursts. They catalogued their durations, energies, and sky positions. What they found was deeply puzzling. The bursts appeared randomly across the sky, with no concentration toward the plane of the Milky Way. That alone suggested an extragalactic origin, or something even more radical. Yet, in the late 1960s, the idea that events outside our galaxy could produce such intense gamma radiation seemed implausible. At that time, even quasars, now known to be among the most luminous objects in the universe, were only beginning to be understood. High-energy astrophysics itself was a young field. X-ray astronomy was barely a decade old. Gamma-ray astronomy, as a discipline, did not yet exist. For years, the mystery remained locked behind classification barriers. The Vela satellites continued to record bursts, accumulating evidence that the universe was doing something violent and unfamiliar. But without public scrutiny, there was no broader theoretical effort to explain them. The data sat in reports read by very few eyes. That changed in 1973. By then, it was clear that the gamma flashes posed no relevance to nuclear weapons monitoring. They were not tests. They were not violations. They were astrophysical. With that determination, the US government declassified the observations, allowing the results to be published openly. The announcement landed like a shockwave through the scientific community. In a short paper published in the astrophysical journal Letters, Kleber-Zadell and his colleagues reported the discovery of cosmic gamma-ray bursts. The wording was cautious, almost understated, but the implications were enormous. Here was a completely new class of astronomical phenomenon, discovered not through a telescope pointed deliberately at the sky, but through instruments designed to catch human violence. The response was immediate and intense. Astronomers around the world scrambled to understand what could possibly generate such flashes. Theoretical papers proliferated. Some proposed nearby neutron stars. Others suggested flaring white dwarfs, supernova shock breakouts, or exotic processes involving antimatter. A few speculated about more radical ideas, including primordial black holes evaporating via Hawking radiation. The lack of precise localization made the problem worse. The Vela satellites could narrow burst positions to large regions of sky, but not to individual stars or galaxies. Without distances, there was no way to determine their true energy scale. A burst from a neutron star in the Milky Way would be impressive. A burst from the edge of the observable universe would be almost inconceivable. This ambiguity dominated gamma-ray burst research for decades. The field was born in uncertainty, shaped by the limitations of instruments that had never been intended for astronomy in the first place. It was a rare example of military surveillance opening an entirely new observational window on the universe. The Cold War, paradoxically, had created the first all-sky gamma-ray observatory. What followed was a slow transformation. Missions were proposed not to monitor treaties, but to study these bursts directly. Detector designs evolved, localization improved, multi-wavelength follow-up became possible. Over time, gamma-ray bursts shifted from classified curiosities to central players in high-energy astrophysics. But their origin story remains a reminder of how science often advances, not through careful planning, but through unexpected signals noticed by people willing to ask the wrong question. The universe had been producing gamma-ray bursts for billions of years. Humanity simply wasn't listening for them until it tried to listen for something else entirely. A gamma-ray burst earns its name not because it is simply bright, but because it obeys a very specific set of physical signatures. Without those signatures, it would dissolve into the background of other high-energy phenomena that constantly flicker across the universe. What separates a true burst from every other gamma-ray source is a combination of duration, spectral behavior, variability, and sheer intensity. features that together define one of the most extreme transient events known in physics. The first defining property is duration. When gamma-ray bursts were first catalogued systematically, it quickly became clear that they did not all last the same amount of time. Some vanished almost as soon as they appeared, lasting only a few milliseconds. Others lingered for tens of seconds, occasionally stretching to minutes. When researchers plotted how long bursts lasted, the distribution did not form a smooth continuum. Instead, it separated into distinct populations. This duration is typically measured using a parameter called T90, which represents the time interval during which 90% of the burst's total detected gamma-ray energy is received. By convention, the clock starts when 5% of the total energy has arrived and stops at 95%. This avoids being misled by faint precursors or weak tails and focuses on the core emission. When thousands of bursts were analysed this way, a striking pattern emerged. One group clustered below about 2 seconds. Another group dominated above that threshold, often lasting tens of seconds. The dividing line at roughly 2 seconds is empirical rather than fundamental, but it has proven remarkably robust. Even as instrumentation improved and sample sizes grew, the bimodal nature of the duration distribution persisted. Duration alone, however, does not fully define a burst. A second key property is spectral hardness. Gamma-ray bursts do not emit all gamma rays equally. Some are dominated by higher energy photons, others by lower energy ones. Spectral hardness quantifies this balance, often expressed as the ratio of high energy counts to low energy counts within a detector's band. When duration and hardness are plotted together, a pattern emerges that reinforces the division. Short bursts tend to be spectrally hard. Their emission is dominated by higher energy gamma rays, often peaking at hundreds of kilo-electron-volts or more. Long bursts are generally softer, with spectra that peak at lower energies and evolve more strongly over time. This correlation is not perfect, but it is statistically significant. It suggests that duration and spectral hardness are not independent properties, but reflections of deeper physical differences in how the bursts are generated. The gamma rays themselves carry clues about the environment in which they were produced, the magnetic fields involved, and the energies of the particles emitting them. Another defining quantity is isotropic equivalent energy. Because gamma-ray bursts are observed as point sources, and because their true geometry is usually unknown at the moment of detection, astronomers initially assume that the emission is isotropic, that it radiates equally in all directions. Under that assumption, they calculate how much energy the burst would have had to release to produce the observed signal at its measured distance. The resulting numbers are extreme. Typical isotropic equivalent energies range from about 10 to the 51 ergs up to 10 to the 54 ergs. To put that in context, the Sun emits roughly 4 times 10 to the 33 ergs per second. Even the lower end of the gamma-ray burst range corresponds to the Sun's total output over millions of years, compressed into seconds. At the upper end, the implied energy rivals the rest mass energy of a star. These numbers immediately signal that something unusual is happening. No known astrophysical object can radiate that much energy isotropically in such a short time. The resolution of this paradox lies in beaming, which will be explored in detail later, but isotropic equivalent energy remains a crucial observational quantity. It allows bursts to be compared consistently and provides an upper bound on the true energy involved. Closely tied to energy is variability. Gamma-ray bursts are not smooth flashes. They're light curves. The plots of brightness versus time are often jagged, asymmetric, and richly structured. Some show a single sharp spike. Others display dozens of overlapping pulses, rising and falling in complex patterns that resemble seismic records more than astronomical signals. The shortest variability timescales observed in some bursts are on the order of milliseconds. This implies that the emitting regions are extraordinarily compact. A source cannot change faster than light can traverse it, so millisecond variability constrains the size of the emitting region to hundreds of kilometers, at most a few hundred miles. That immediately excludes ordinary stars and even most stellar remnants unless relativistic effects are involved. Variability also carries information about the emission mechanism. Rapid fluctuations suggest internal processes within a relativistic outflow, such as collisions between shells moving at different speeds or magnetic reconnection events that release energy suddenly. Slower, smoother components are more consistent with interactions between the outflow and the surrounding medium. The coexistence of both in many bursts hints at layered physical processes unfolding on different scales. Light curve complexity is another hallmark. No two gamma-ray bursts look exactly alike. Some exhibit a fast rise followed by a slower decay, a shape known as a Fred, fast rise, exponential decay. Others show multiple peaks with no obvious symmetry. Some display precursor emission seconds before the main burst, while others show extended emission long after the initial spike. Despite this diversity, statistical patterns emerge when large samples are analysed. Pulse widths tend to broaden at lower energies. High-energy emission often peaks earlier than low-energy emission, a phenomenon known as spectral lag. These correlations are not arbitrary. They encode information about how particles are accelerated, how radiation is produced, and how relativistic motion distorts time and energy as seen by a distant observer. The fact that gamma-ray bursts are defined by such fleeting, high-energy signals explains another essential aspect of their nature. They must be detected from space. Earth's atmosphere is extremely effective at blocking gamma rays. That shielding is a gift to life, but a barrier to astronomy. Gamma rays interact with atmospheric molecules through pair production and scattering, losing their energy long before they can reach the ground. As a result, no ground-based telescope can directly observe the prompt emission of a gamma-ray burst. Detection requires instruments placed above the atmosphere, typically aboard satellites in low Earth orbit or beyond. These detectors do not focus gamma rays in the way optical telescopes focus visible light. Instead, they rely on scintillators or semiconductor detectors that register individual photon interactions, converting gamma rays into electrical signals. This detection method shapes what we can know. Gamma-ray instruments often have wide fields of view, sometimes covering most of the sky at once, but relatively poor angular resolution. They excel at catching transient events, but struggle to pinpoint their exact locations. Early gamma-ray burst detectors could localize bursts only to regions of sky-spanning degrees, far too large to identify a host galaxy or counterpart at other wavelengths. Despite these limitations, space-based detection is indispensable. The atmosphere does not merely attenuate gamma rays, it effectively defines the observational boundary between gamma-ray astronomy and every other wavelength regime. Without satellites, gamma-ray bursts would remain invisible no matter how powerful they are. The need for space-based detection also introduces selection effects. Instruments are sensitive only within certain energy ranges. Bursts that peak outside those ranges may be undercounted or missed entirely. Very soft bursts may resemble X-ray flashes. Extremely hard bursts may deposit energy inefficiently in some detectors. Understanding what makes a burst therefore requires careful accounting of instrumental biases. As detectors improved, new subtleties emerged. Some events blur the boundaries. Ultra-long bursts last thousands of seconds. Low-luminosity bursts resemble ordinary supernovae more than classical gamma-ray bursts. X-ray flashes challenge the notion that gamma rays must dominate the emission. Each of these variations forces refinements to the definitions without erasing the core properties. What ultimately defines a gamma-ray burst is not a single number or threshold, but a convergence of extremes. A burst is brief on cosmic timescales. It is spectrally hard, dominated by high-energy photons. It is violently variable, structured down to milliseconds. It carries an implied energy budget that strains intuition. and it announces itself in gamma rays that only instruments in space can see. These defining properties are not just descriptive, they act as constraints. Any viable physical model must explain all of them at once, without contradiction. It must account for how such energy is generated, how it is collimated, how it escapes, and why it varies so rapidly. Gamma-ray bursts are therefore not just objects of study, they are stress tests for fundamental physics. Understanding what makes a burst sets the stage for the deeper question that follows naturally from these observations. If these properties are real, and the data leave little room for doubt, what kind of astrophysical systems can possibly produce them? When enough gamma-ray bursts had been recorded to treat them statistically rather than anecdotally, an unexpected structure emerged. The population did not form a smooth continuum of durations and properties. Instead, it split. One group clustered tightly around very short timescales, the other spread broadly across longer ones. The dividing line appeared near 2 seconds, a boundary that at first seemed arbitrary, but soon proved to reflect something fundamental about how these events are made. This separation was not imposed by theory, it was discovered empirically. When researchers plotted burst duration against the number of detected events, the histogram showed 2 peaks. One peak lay below about 2 seconds, the other extended from a few seconds to tens of seconds, sometimes longer. The valley between them was real, not a statistical artifact. As instruments improved and the sample grew from dozens to hundreds and then thousands of bursts, the bimodal structure remained. The parameter used to define this split, T90, captures the time interval over which most of the gamma-ray energy arrives. For short bursts, T90 often falls below half a second, sometimes as low as a few tens of milliseconds. For long bursts, T90 typically ranges from several seconds to more than a minute. The 2-second boundary is a convention rather than a hard physical cutoff, but it efficiently separates two populations with distinct behaviors. Duration alone would not justify treating these as fundamentally different phenomena. What made the division meaningful was that other properties followed the same split. Spectral hardness, variability, host environments, and redshift distributions all correlated with duration in ways that were difficult to ignore. Short bursts, on average, are spectrally harder. Their gamma-ray emission is dominated by higher energy photons, with peak energies often exceeding several hundred kilo-electron volts. Their light curves are compact and sharply structured, sometimes consisting of a single spike or a brief cluster of spikes. Long bursts tend to be spectrally softer, with more pronounced spectral evolution and extended emission at lower energies. The physical meaning of this division became clearer only when precise localizations became possible. For decades after their discovery, gamma-ray bursts could not be pinned down well enough to identify their host galaxies. That changed in the late 1990s, when rapid follow-up observations revealed afterglows at X-ray, optical, and radio wavelengths. For the first time, astronomers could associate bursts with specific galaxies and measure their distances. Long bursts were the first to yield these breakthroughs. Their afterglows were brighter and longer lasting, making them easier to study. When their host galaxies were identified, a pattern emerged. Long bursts overwhelmingly occur in star-forming galaxies. Many are found in irregular or dwarf galaxies with high rates of massive star formation. Within those galaxies, long bursts tend to occur in regions rich in young, massive stars rather than in older stellar populations. This association pointed toward a stellar origin tied to short-lived progenitors. Massive stars live fast and die young. They do not wander far from their birthplaces before collapsing. The environments of long bursts, dense, gas-rich, actively forming stars, fit that expectation precisely. Short bursts told a different story. When their afterglows were finally localized with sufficient accuracy, their host galaxies displayed a much wider diversity. Some short bursts occur in star-forming galaxies, but many are found in elliptical galaxies with little or no ongoing star formation. Others appear far from the centres of their hosts, sometimes tens of kiloparsecs from the nearest visible galaxy, corresponding to tens of thousands of light-years. This spatial offset is a crucial clue. Elliptical galaxies are dominated by old stellar populations. They have not formed massive stars for billions of years. Any event occurring there cannot depend on a short-lived progenitor. The large offsets observed for some short bursts suggest systems that received substantial kicks early in their evolution and then wandered for long periods before producing a burst. Redshift distributions reinforce this distinction. Long bursts are observed across a wide range of redshifts, including some of the most distant events ever detected. Many occurred when the universe was only a fraction of its current age. This aligns with the cosmic history of star formation, which peaked several billion years ago and was more intense in the early universe. Long bursts track that history remarkably well. Short bursts, by contrast, are typically observed at lower redshifts. They are, on average, closer to Earth. This does not mean they are intrinsically weaker, but rather that their progenitors take time to form. Systems capable of producing short bursts may require hundreds of millions to billions of years to evolve before releasing their energy. As a result, they are more common in the relatively mature universe. The energy release mechanisms also differ in subtle but important ways. Long bursts tend to have higher total isotropic equivalent energies on average, though there is significant overlap between the two populations. Long bursts often release their energy over extended periods, with complex light curves and prolonged afterglow emission. Short bursts release their energy more abruptly, with less total gamma-ray output but higher peak luminosities in some cases. The environments in which these bursts occur influence how their energy is dissipated. Long bursts explode within dense regions shaped by stellar winds and previous generations of stars. Their relativistic jets interact with this material, producing bright afterglows that can be followed for days or weeks. Short bursts often occur in lower density environments, leading to fainter and faster fading afterglows that are more difficult to detect. These observational differences forced theorists to confront an uncomfortable conclusion. There is no single mechanism responsible for all gamma-ray bursts. The universe is producing at least two distinct kinds of catastrophic events that manifest as gamma-ray flashes. For long bursts, the emerging picture involved the deaths of massive stars. When a star far more massive than the Sun exhausts its nuclear fuel, its core collapses. Under certain conditions, that collapse leads not merely to a supernova, but to the formation of a compact object, likely a black hole, surrounded by a dense, rapidly accreting disk. Energy extracted from this system powers narrow, relativistic jets that punch through the star's outer layers. When those jets break free, they produce the gamma rays we detect as a long burst. Short bursts required a different explanation. The old stellar populations, large offsets, and delayed occurrence all pointed toward compact binary systems. Neutron stars, the dense remnants of supernova explosions, can form in pairs. Over time, these pairs lose energy through gravitational radiation, spiraling closer together over millions or billions of years. When they finally merge, the collision releases enormous energy in a very short time, naturally producing a brief gamma-ray flash. This distinction is not merely academic, it reflects two fundamentally different pathways by which the universe concentrates and releases energy. One pathway is tied to the life cycle of massive stars and the ongoing process of star formation. The other is tied to the long-term evolution of compact objects and the slow dance of gravity over cosmic time. Despite these differences, there is overlap. Some long bursts are unusually short. Some short bursts exhibit extended emission. Nature rarely respects clean categorical boundaries, but the statistical separation remains meaningful because it captures dominant trends rather than absolute rules. The 2-second division also highlights how gamma-ray bursts challenge intuition. A difference of a few seconds may seem trivial in everyday life. In high-energy astrophysics, it separates phenomena driven by stellar collapse from those driven by compact object mergers. Time, in this context, is not just a measure of duration. It is a diagnostic tool that encodes the size, structure, and evolution of the engine producing the burst. Understanding the short-long distinction reshaped gamma-ray burst research. It allowed observations to be interpreted within coherent physical frameworks rather than as isolated curiosities. It connected bursts to other astrophysical phenomena. Supernova on one hand, gravitational wave sources on the other, integrating them into a broader picture of how extreme events shape the universe. Yet the division also raised new questions. Why do only some massive stars produce long bursts? Why do some mergers produce detectable gamma rays while others remain dark? What determines whether a relativistic jet successfully escapes its environment? These questions sit at the boundary between observation and theory, where data constrain models but do not yet fully determine them. The realization that gamma-ray bursts come in at least 2 distinct varieties marked a turning point. It transformed the field from one defined by mystery into one defined by structure. But that structure is only the beginning. To understand why these 2 populations exist at all and how they operate at such extreme energies, we have to look more closely at the physical engines driving each class. The story of long gamma-ray bursts begins not with a flash, but with a star that has spent millions of years quietly holding itself together against gravity. Massive stars live fast lives. A star with 20, 30, or more times the mass of the Sun burns through its nuclear fuel at a ferocious rate. Hydrogen fuses into helium, helium into carbon and oxygen, then onward through progressively heavier elements. Each stage is shorter than the last. What took millions of years at the beginning is reduced to mere days near the end. Eventually, the core becomes layered like an onion, with iron at the center. Iron is the end of the road. Fusing iron does not release energy, it consumes it. Once an iron core forms and grows beyond a critical mass, the star loses its last source of internal support. Gravity wins. In an ordinary massive star, this moment triggers a core collapse supernova. The core implodes, rebounds, and launches a shock wave that tears the star apart. But long gamma-ray bursts are not ordinary supernovae. They represent a rare and far more extreme outcome of stellar death. The collapsar model was developed to explain this outcome. The term collapsar refers to a collapsing star whose core does not halt its implosion, but instead forms a black hole directly. For this to happen, several conditions must be met simultaneously. The star must be massive enough that the core exceeds the maximum mass of a neutron star. It must retain sufficient angular momentum to form a disk rather than collapsing spherically, and it must have lost much of its outer hydrogen envelope before collapse. These requirements already eliminate most stars. Only a small fraction of massive stars satisfy them, which immediately explains why long gamma-ray bursts are so rare compared to ordinary supernovae. When such a star collapses, the iron core falls inward at a substantial fraction of the speed of light. Densities climb beyond nuclear values. If the mass and rotation are sufficient, the core does not stabilize as a neutron star. Instead, an event horizon forms. A black hole is born at the center of the star. This is not the end of the story. It is the beginning. Surrounding the newborn black hole is a vast amount of infalling stellar material. Because the progenitor star was rotating, this material cannot fall straight in. Conservation of angular momentum forces it into a flattened structure, an accretion disk. This disk may be only a few thousand kilometers across, on the order of a few thousand miles, but it contains several solar masses of matter spiraling inward at an extraordinary rate. The accretion rate is extreme by any astrophysical standard. matter may fall into the black hole at rates of tenths of a solar mass per second. Friction, magnetic turbulence, and relativistic effects heat the disk to enormous temperatures. Neutrinos flood outward. Magnetic fields are amplified to strengths trillions of times stronger than Earth's. This disk black hole system is the engine of a long gamma-ray burst. Energy is extracted from the system in two primary ways. One involves the gravitational energy released as matter spirals inward through the accretion disk. The other involves rotational energy extracted from the spinning black hole itself through magnetic fields anchored in the disk. In both cases, the energy does not emerge isotropically. It is funneled along the rotation axis of the system. Along that axis, a pair of narrow, oppositely directed jets form. These jets are not gentle outflows, they are relativistic, with bulk Lorentz factors of hundreds, meaning the material is moving at more than 99.9% of the speed of light. They are also extremely collimated, with opening angles of only a few degrees. This collimation is essential. Without it, the energy would be diluted and no burst would be visible across cosmic distances. At first, the jets are buried deep inside the dying star. The progenitor may have a radius of several 100,000 kilometers, hundreds of thousands of miles. The jets must drill their way through this material before they can escape. This is one of the most violent and unstable phases of the process. As the jets propagate outward, they shock, heat, and displace stellar matter. A cocoon of hot plasma forms around them, exerting pressure that helps collimate the flow. If the jets are powerful and persistent enough, they break out of the star's surface. If they fail, if the engine shuts off too soon or the star is too extended, the jets stall and dissipate, producing no gamma-ray burst at all. This jet breakout is a critical moment. Only after escaping the star can the jets accelerate freely and become transparent to their own radiation. Only then can gamma rays escape into space. The gamma ray burst itself is produced not at the black hole and not at the stellar surface, but farther out, at distances of millions to billions of kilometers from the engine, millions to hundreds of millions of miles. In this region, internal shocks or magnetic dissipation within the jet convert kinetic or magnetic energy into radiation. Electrons are accelerated to extreme energies and emit gamma rays through synchrotron radiation and related processes. The duration of the burst reflects the lifetime of the central engine. As long as material continues to fall into the accretion disk and power the jets, gamma rays are produced. In long bursts, this process can last tens of seconds. When the accretion rate drops, or the disk is exhausted, the jets weaken and the prompt emission ends. Meanwhile, the rest of the star is being destroyed. The interaction between the jets and the stellar envelope deposits enormous energy into the surrounding material. This produces a highly energetic supernova, often referred to as a hypernova. Observationally, many long gamma-ray bursts are associated with unusually bright and energetic supernova detected days to weeks later at optical wavelengths. These supernovae are not incidental, they are part of the same event. The gamma-ray burst marks the successful escape of the jets. The supernova marks the unbinding of the star as a whole. Yet only a tiny fraction of core collapse supernova produce gamma-ray bursts. This scarcity is not mysterious when the conditions are considered carefully. First, the star must be rapidly rotating at the moment of collapse. Many massive stars lose angular momentum through stellar winds or interactions with companion stars. Without sufficient rotation, an accretion disk does not form and no jets are launched. Second, the star must have lost its outer hydrogen envelope. If the envelope is too extended, the jets cannot punch through before the engine shuts off. This is why long gamma-ray burst progenitors are often identified as stripped envelope stars, such as Wolf-Rayet stars, which have already shed their outer layers. Third, the metallicity of the star matters. Stars with lower metal content tend to have weaker stellar winds and therefore retain more angular momentum. Observationally, long gamma-ray bursts are more common in low metallicity environments, consistent with this requirement. Finally, geometry plays a decisive role. Even if a star produces a successful jet, the burst is visible only if one of the jets is pointed toward Earth. Because the jets are narrow, most bursts go unseen. For every long gamma-ray burst detected, many more occur with their beams aimed elsewhere. Taken together, these factors explain why long gamma-ray bursts are both rare and extreme. They are not a generic outcome of stellar death. They represent a specific failure mode of massive stars under particular conditions, amplified by relativistic beaming. From a physical standpoint, collapses are laboratories for physics under extreme conditions. They involve black hole formation in real time, accretion at extraordinary rates, magnetic fields far beyond terrestrial experience, and matter accelerated to near-light speed. Few phenomena test our understanding of gravity, plasma physics, and relativity so severely. They also link gamma-ray bursts to the broader life cycle of stars and galaxies. Long bursts trace regions of intense star formation. Their redshift distribution mirrors the cosmic history of massive star birth. In this sense, they are not merely exotic fireworks. They are signposts of where and when the universe has been most actively forming its most massive stars. At the same time, collapsars highlight how narrow the path is between the ordinary and the extraordinary. Most massive stars end their lives quietly by cosmic standards, producing supernovae that, while impressive, do not dominate the universe. A few, under just the right conditions, channel their death into a focused beam of radiation that can be seen across billions of light years. The collapsar model explains why long gamma-ray bursts exist at all, but it also underscores their improbability. They are the outcome of precise alignments in mass, rotation, composition, and geometry. When those alignments occur, the result is one of the brightest moments the universe can offer. Short gamma-ray bursts originate in systems that have been evolving quietly for hundreds of millions, sometimes billions, of years before releasing their energy in a fraction of a second. Unlike long bursts, which mark the immediate death of massive stars, short bursts are the delayed consequences of stellar death. Signals produced long after the original stars have vanished, leaving behind only their most compact remnants. The protagonists are neutron stars and black holes. A neutron star is what remains when a massive star collapses but does not quite cross the threshold to become a black hole. Roughly 1 to 2 times the mass of the Sun is crushed into a sphere about 20 kilometers across, around 12 miles. Matter inside is packed so densely that atomic nuclei touch. A teaspoon of neutron star material would weigh billions of tons. Gravity is intense, magnetic fields are extreme, and rotation can be rapid, with some neutron stars spinning hundreds of times per second. Neutron stars are often born in pairs. Many massive stars form in binary systems, and if both stars are heavy enough, each may undergo core collapse, leaving behind 2 neutron stars locked in orbit around one another. Alternatively, one star may collapse into a neutron star, while the other later collapses into a black hole, forming a mixed pair. In either case, the result is a compact binary system held together by gravity and slowly evolving under the influence of a subtle but relentless process. That process is gravitational radiation. According to general relativity, accelerating masses distort space-time and emit gravitational waves. For wide binary systems, this effect is negligible. But for compact objects like neutron stars and black holes, orbiting at close distances, gravitational wave emission becomes significant. Energy is carried away from the system, and the orbit shrinks. The objects spiral toward each other imperceptibly at first, then more rapidly as they draw closer. This in-spiral can last for hundreds of millions or billions of years. During that time, the system may drift far from its birthplace. Supernova explosions that formed the neutron stars can impart velocity kicks of hundreds of kilometers per second, hundreds of miles per second, sending the binary wandering through its host galaxy or even into intergalactic space. By the time the merger occurs, the system may be far removed from any visible stellar nursery. Eventually, the separation becomes small enough that the in-spiral accelerates dramatically. In the final seconds, the orbital frequency rises into the tens or hundreds of hertz. Gravitational waves grow stronger and sweep upward in frequency in a characteristic chirp. This is the moment when detectors like LIGO and Virgo become sensitive to the signal, registering tiny distortions in space-time caused by objects colliding hundreds of millions of light-years away. Then, the merger happens. For a binary neutron star system, the final coalescence is violent and complex. As the stars draw within a few tens of kilometers of each other, tidal forces become extreme. Each star distorts the other, stretching and squeezing its dense matter. Depending on the masses and internal physics of the neutron stars, several outcomes are possible. In some cases, the merged object collapses almost immediately into a black hole. In others, it forms a hypermassive neutron star, temporarily supported against collapse by rapid rotation and thermal pressure. This object may survive for milliseconds to seconds before collapsing. In rare cases, a massive neutron star may remain stable for much longer. Regardless of the exact path, the merger liberates enormous energy. Gravitational binding energy is released, magnetic fields are twisted and amplified, neutrinos pour out in staggering numbers, and crucially for gamma-ray bursts, some fraction of the surrounding matter does not fall directly into the central remnant. Instead, it forms a dense accretion disk. This disk contains a fraction of a solar mass of neutron-rich material orbiting at relativistic speeds within tens of kilometers of the central object. As in the collapsar scenario, extreme conditions reign. Temperatures exceed billions of degrees. Magnetic fields reach extraordinary strengths. The disk evolves rapidly, accreting onto the central remnant over timescales of milliseconds to seconds. From this compact engine, narrow relativistic jets can be launched. The exact mechanism by which these jets form is still an area of active research, but the broad outlines are clear. Strong magnetic fields, anchored in the disk and threading the central object, extract energy and channel it along the rotation axis. Neutrino-antineutrino annihilation may also contribute, depositing energy above the poles of the system. The result is a pair of oppositely directed jets, accelerating outward at velocities approaching the speed of light. Because the central engine is smaller and shorter-lived than in collapsers, the jets are briefer. They punch through whatever debris surrounds the merger site and emerge into space for only a short time. This naturally produces a short gamma-ray burst, with durations typically below 2 seconds and often well under 1 second. The compactness of the system explains the hardness of the emission. Short bursts tend to peak at higher gamma-ray energies than long bursts. The jets are launched from deeper gravitational potentials over shorter timescales, with higher characteristic energies per particle. The resulting gamma rays reflect that intensity. Neutron star-black hole mergers follow a similar but not identical path. In these systems, a neutron star orbits a black hole. As the in-spiral proceeds, tidal forces from the black hole can tear the neutron star apart before it crosses the event horizon. Whether this happens depends on the masses involved and the spin of the black hole. If the neutron star is swallowed whole, little matter remains outside to form a disk, and no gamma-ray burst is expected. If tidal disruption occurs first, a disk forms and a short burst becomes possible. This sensitivity to parameters explains why not all compact object mergers produce observable gamma-ray bursts. Geometry matters, orientation matters, internal structure matters. The same type of system can yield dramatically different outcomes, depending on details measured in kilometers and milliseconds. For decades, the connection between short gamma-ray bursts and compact object mergers was theoretical, supported indirectly by host galaxy demographics and energetics. The decisive confirmation came only recently, with the advent of gravitational wave astronomy. In August 2017, detectors recorded a gravitational wave signal from a binary neutron star merger. The signal lasted tens of seconds, sweeping upward in frequency exactly as predicted by general relativity. Just 1.7 seconds after the merger time inferred from the gravitational waves, a short gamma-ray burst was detected by space-based gamma-ray observatories. This temporal coincidence was extraordinary. For the first time, two fundamentally different messengers, gravitational waves and gamma rays, were observed from the same cosmic event. The delay of less than 2 seconds placed tight constraints on the speed of gravity, the structure of the jet, and the physics of the emission. Follow-up observations across the electromagnetic spectrum revealed additional components. Optical and infrared telescopes observed a kilonova, powered by the radioactive decay of heavy elements synthesized in the merger ejector. X-ray and radio emission followed as the jet interacted with surrounding material. Together, these signals painted a coherent picture of a neutron star merger producing a short gamma-ray burst. This event transformed short gamma-ray bursts from speculative phenomena into well-established consequences of compact object mergers. It also connected them directly to one of the most profound predictions of general relativity. Short bursts are therefore not isolated curiosities. They are part of a larger physical narrative that includes gravitational wave emission, relativistic jet formation, and the creation of the heaviest elements in the periodic table. Gold, platinum, and other R-process elements are forged in the neutron-rich debris ejected during these mergers. The same event that produces a brief flash of gamma rays also seeds galaxies with material that will later become planets, jewelry, and electronics. The environments of short bursts reflect this origin. They are found in both young and old galaxies, in regions with little gas and far from star-forming regions. Their afterglows are often faint because the surrounding medium is sparse. Their occurrence rate tracks not star formation directly, but the integrated history of star formation, delayed by the long in-spiral times of compact binaries. From a physical perspective, short gamma-ray bursts represent one of the cleanest laboratories for studying matter and space-time under extreme conditions. The masses involved are precisely measurable through gravitational waves. The timescales are short, the geometry is constrained. Each detection allows tests of relativity, nuclear physics, and plasma dynamics that are impossible in any terrestrial experiment. They also underscore a central theme of gamma-ray burst science. Brevity does not imply simplicity. A burst lasting a few tenths of a second may encode the dynamics of neutron-rich matter, the behavior of magnetic fields under extreme strain, and the propagation of relativistic jets through complex debris fields. Time, in these events, is compressed, but information-rich. Short gamma-ray bursts are the universe's way of announcing that two of its most extreme objects have finally met after a long gravitational courtship. The flash is brief, but it marks a transformation that reshapes space-time itself, sending ripples and radiation across the cosmos in perfect synchrony. Everything about gamma-ray bursts becomes more intelligible once the jets are taken seriously, not as side effects, but as the central physical structure of the event. Without relativistic jets, gamma-ray bursts would be impossible. The raw energy requirements inferred from early observations were so extreme that, taken at face value, they bordered on the unphysical. Some bursts appeared to release more energy in seconds than the Sun could produce over its entire lifetime. Others rivaled the binding energy of a neutron star. For a time, this led to speculation that gamma-ray bursts might involve entirely new physics. In reality, the solution lay not in exotic energy sources, but in geometry and relativity. Gamma-ray bursts are not spherical explosions. They are highly collimated, relativistic outflows, jets, that concentrate energy into narrow beams and fling it outward at velocities astonishingly close to the speed of light. To understand why this matters, consider motion at relativistic speeds. In everyday life, velocities add linearly, At relativistic speeds, they do not. Instead, special relativity introduces the Lorentz factor, usually denoted by the symbol gamma. The Lorentz factor quantifies how strongly time, length, and energy are distorted for an object moving close to light speed. A Lorentz factor of 1 corresponds to rest. A Lorentz factor of 10 corresponds to motion at about 99.5% of the speed of light. A Lorentz factor of 100 corresponds to about 99.995%. Gamma-ray burst jets typically require Lorentz factors of hundreds, sometimes inferred to exceed 300 or even 1,000 in extreme cases. These numbers are not arbitrary. They are demanded by the observations. If the outflow were slower, the intense gamma radiation would interact with itself. High-energy photons colliding head-on can produce electron-positron pairs, making the region opaque. This compactness problem would trap radiation and soften the spectrum, contradicting what is observed. Relativistic motion solves this by beaming photons forward, reducing their interaction angles and allowing them to escape. Relativistic motion also compresses time. Variability that occurs over seconds in the jet's own frame can appear compressed into milliseconds for a distant observer. This explains how compact engines can produce the rapid fluctuations seen in burst-light curves without violating causality. But speed alone is not enough. The energy must be organized. Gamma-ray burst jets are extraordinarily collimated. Typical opening angles are only a few degrees, sometimes less. To visualize this, imagine a flashlight beam that narrows until it illuminates only a tiny patch on a distant wall. Now imagine that flashlight emits the power of a star. This collimation changes everything about how we interpret the burst. The isotropic equivalent energy assumes radiation goes in all directions. In reality, the true energy is reduced by the beaming factor, the fraction of the sky covered by the jet. A jet with an opening angle of 5 degrees covers less than 1% of the sky. Narrower jets cover far less. When this correction is applied, the true energy budgets of gamma-ray bursts fall into a more physically reasonable range. Still extreme, but compatible with what can be extracted from accretion disks and spinning black holes. The universe is not producing impossible amounts of energy. It is aiming energy very precisely. Jet formation itself is a consequence of rotation and magnetic fields. Both collapses and compact object mergers produce rapidly rotating central engines surrounded by dense magnetized disks. Magnetic field lines threading the disk and the central object are twisted by rotation, storing enormous energy. Along the rotation axis, where matter density is lowest, these fields can accelerate plasma outward, forming a jet. Once launched, the jet is not a smooth, steady flow. It is dynamic, structured, and unstable. Variations in the central engine, changes in accretion rate, magnetic field configuration, or rotation are imprinted onto the jet as fluctuations in velocity and density. Faster portions of the jet catch up with slower ones. Magnetic fields tangle and snap. Energy is dissipated internally before the jet ever encounters its surroundings. This leads to one of the central questions in gamma-ray burst physics. How is the prompt gamma-ray emission actually produced? Two broad classes of models dominate the discussion. The first involves internal shocks. In this picture, the jet consists of shells or blobs of plasma launched at slightly different speeds. When a faster shell collides with a slower one ahead of it, a shock forms. Particles are accelerated in the shock, magnetic fields are amplified, and gamma rays are emitted, typically through synchrotron radiation and related processes. Internal shocks have intuitive appeal. They naturally produce variability. They explain why emission occurs far from the central engine, where the jet has expanded and become transparent. But they are inefficient. Only a small fraction of the jet's kinetic energy is converted into radiation in this process. That inefficiency becomes problematic when trying to match observed luminosities. The second class of models invokes magnetic reconnection. In this picture, the jet is initially dominated by magnetic energy rather than kinetic energy. Magnetic field lines carried outward by the flow are twisted, sheared, and compressed. When oppositely directed, field lines are forced together, they reconnect, releasing stored magnetic energy explosively. This energy accelerates particles directly, producing radiation without relying on strong shocks. Magnetic reconnection can be far more efficient than internal shocks. It can operate rapidly and intermittently, producing complex light curves. It naturally accommodates high Lorentz factors and strong polarization signals observed in some bursts. However, it requires the jet to remain magnetically dominated over large distances, which places constraints on how jets form and evolve. Current evidence suggests that reality may not choose one mechanism exclusively. Some bursts may be shock-dominated, others may be magnetically dominated. In many cases, both processes may operate at different stages or in different regions of the jet. The diversity of observed light curves hints at a diversity of internal jet physics. Regardless of the dissipation mechanism, relativistic beaming profoundly shapes what we see. Because the jet is moving toward us at nearly light speed, radiation is concentrated into a narrow cone, even smaller than the physical opening angle of the jet. This is relativistic aberration. Photons emitted at a wide range of angles in the jet's frame are squeezed into a tight beam in the observer's frame. As a result, only observers located within a small angular window can see the burst at all. This has two consequences. First, it explains the apparent rarity of gamma-ray bursts. Most jets are simply not aimed at Earth. For every burst detected, many more occur unseen. Second, it explains why observed bursts appear so luminous. Beaming amplifies the apparent brightness by orders of magnitude. Time is also distorted. Emission from different parts of the jet arrives compressed in time. This enhances variability and sharpens features in the light curve. Even modest fluctuations in the engine can appear dramatic once relativistic effects are taken into account. Beaming also explains correlations between different observational properties. For example, bursts with narrower jets tend to appear brighter and more variable. Bursts viewed slightly off-axis appear dimmer, softer, and longer. In some cases, we may detect only the afterglow of a jet whose core was not pointed directly at us, missing the prompt gamma rays entirely. This off-axis viewing has become especially important in the era of gravitational wave astronomy. Compact object mergers detected through gravitational waves may produce jets that are not perfectly aligned with Earth. In such cases, the gamma-ray burst may be weak or delayed, while the afterglow brightens gradually as the jet slows and spreads. These observations provide independent constraints on jet structure and beaming geometry. Extreme collimation also helps explain why gamma-ray bursts can coexist with their environments. A star undergoing collapse or a merger ejects enormous amounts of matter in all directions. If energy were released isotropically, it would be choked by this debris. Jets exploit the path of least resistance, carving channels through which energy can escape without being smothered. From a broader perspective, relativistic jets unify gamma-ray bursts with other high-energy astrophysical systems. Active galactic nuclei, microquasars, and some tidal disruption events also produce relativistic jets. The scales differ enormously, from stellar mass black holes to supermassive ones, but the underlying physics of rotation, magnetic fields, and relativistic outflows is strikingly similar. Gamma-ray bursts represent the most extreme end of this family. Their jets are shorter-lived, more tightly collimated, and faster than almost any others observed. They push known acceleration mechanisms to their limits. If a theory can explain gamma-ray burst jets, it can likely explain relativistic jets elsewhere. Ultimately, beaming is what allows gamma-ray bursts to exist as observable phenomena. Without it, their energy requirements would be implausible. With it, they become natural, still extraordinary, but physically grounded, consequences of compact, rapidly rotating engines operating under extreme conditions. The brightest moments in the universe are not bright because they are wasteful. They are bright because they are precise. The jets explain how energy is launched and aimed, The prompt emission explains how that energy becomes gamma rays. This is the most technically difficult part of gamma-ray burst physics, and the place where observation and theory still do not fit together cleanly. The data are rich, precise, and abundant. The interpretations remain contested. What is clear is that the gamma rays we observe are not produced at the central engine itself. They are generated farther out, once the jet has expanded, accelerated, and become transparent enough for radiation to escape. The prompt emission is the initial flash of gamma rays, the signal that defines the burst. It lasts from milliseconds to minutes and contains most of the burst's radiated energy. Whatever mechanism produces it must operate efficiently, rapidly, and under extreme relativistic conditions. The most widely discussed mechanism is synchrotron radiation. Synchrotron radiation occurs when charged particles, typically electrons, are accelerated sideways by magnetic fields. In everyday environments, synchrotron emission produces radio waves, or visible light. In gamma-ray bursts, the magnetic fields and particle energies are so extreme that the same process produces gamma rays. Inside a relativistic jet, electrons are accelerated to energies many orders of magnitude higher than those achievable in terrestrial accelerators. Magnetic fields can reach strengths of hundreds of thousands to millions of Gauss. Under these conditions, electrons spiral tightly along magnetic field lines and emit radiation across a broad spectrum. When the characteristic energies are high enough, the emission naturally falls in the gamma-ray band. Synchrotron radiation has several attractive features. It is efficient. It produces non-thermal spectra consistent with observations showing that gamma-ray burst spectra are not simple blackbodies. It naturally explains rapid variability, since particle acceleration can occur in localized regions that evolve quickly, and it arises almost inevitably in any magnetized relativistic plasma. For many years, synchrotron emission was treated as the default explanation for the prompt emission. However, detailed observations revealed problems. One of the most serious issues concerns the low-energy spectral slope. Simple synchrotron theory predicts a characteristic shape for the spectrum below its peak energy. In many bursts, the observed spectra are too hard, too flat, to be easily reconciled with standard synchrotron models. This discrepancy is known as the synchrotron line of death problem. Attempts to resolve this have led to increasingly sophisticated models. Some invoke rapidly cooling electrons in evolving magnetic fields. Others consider anisotropic pitch angle distributions, where electrons do not spiral isotropically. Still others modify the acceleration process itself. While progress has been made, no single synchrotron-based model has convincingly explained the full diversity of observed spectra. This motivated renewed interest in a second mechanism, inverse Compton scattering. In inverse Compton processes, high-energy electrons collide with lower-energy photons and transfer energy to them. The photons are boosted to much higher energies, potentially into the gamma-ray range. In gamma-ray bursts, the seed photons may come from synchrotron emission itself or from thermal radiation originating closer to the central engine. Inverse Compton scattering can dramatically reshape the spectrum. It can produce hard gamma-ray components and extend emission to very high energies. In some bursts, observations from space-based gamma-ray telescopes have detected photons with energies reaching into the tens of giga-electron volts, far above the typical spectral peak. Inverse Compton processes offer a natural way to produce such emission. However, inverse Compton models introduce their own challenges. They require a sufficient density of seed photons and electrons in the right energy ranges. They must operate without suppressing the synchrotron component entirely, and they must reproduce the observed temporal correlations between low energy and high energy light curves. In many cases, inverse Compton emission appears to be present but not dominant. A third class of models focuses on photospheric emission. The photosphere of a gamma-ray burst jet is the surface from which photons can escape freely. Below this radius, the jet is opaque. Photons scatter repeatedly and remain trapped. Above it, the density drops enough that radiation streams outward. If the jet carries significant thermal energy from its base, this energy can emerge as quasi-thermal radiation at the photosphere. In its simplest form, this would produce a black body spectrum. Early observations did not show clean black bodies, leading to skepticism about photospheric models. But improved data revealed that many bursts do contain a thermal component, often hidden beneath broader non-thermal emission. Photospheric emission has several appealing properties. It is highly efficient, converting a large fraction of the jet's energy into radiation. It naturally produces a spectral peak at energies consistent with observations. It avoids some of the synchrotron spectral slope problems. And it ties the emission directly to the bulk properties of the jet rather than to poorly constrained microphysics. The difficulty lies in explaining the observed complexity. Gamma-ray burst spectra are rarely simple. They evolve rapidly. The peak energy shifts during the burst, often decreasing with time. Light curves show multiple pulses with different spectral properties. A pure photospheric model struggles to reproduce this richness without additional processes. As a result, many modern models are hybrid. Thermal photons emerge from the photosphere and then undergo additional processing. They may be upscattered by relativistic electrons through inverse Compton interactions. They may mix with synchrotron emission from regions farther out in the jet. The observed spectrum becomes a superposition of components, each shaped by different physics. Spectral evolution is one of the strongest constraints on any prompt emission model. In most bursts, the characteristic energy at which the spectrum peaks decreases over time. This hard-to-soft evolution is not subtle. It appears consistently across many events. Early pulses are harder. Later pulses are softer. Any successful model must explain why the emission evolves in this way. Several mechanisms can contribute. The jet may be decelerating as it interacts internally. Magnetic fields may weaken with distance. Particle acceleration may become less efficient. The photosphere may move outward as the jet expands. All of these effects can shift the characteristic photon energy downward over time. Temporal correlations between different energy bands add further constraints. In many bursts, high-energy emission peaks earlier than low-energy emission. Spectral lags on the order of milliseconds to seconds are common. These lags encode information about emission regions, relativistic geometry, and radiation processes. Another critical constraint comes from polarization. Some gamma-ray bursts show evidence of significant polarization in their prompt emission. Polarization implies ordered magnetic fields and anisotropic emission regions. This favors magnetically dominated models and challenges scenarios where shocks completely randomize field orientations. High-energy observations have added another layer of complexity. Some bursts exhibit delayed emission at energies above a Geiger electron volt, appearing seconds after the main gamma-ray flash. This delayed component often lasts much longer than the prompt emission. Its origin may differ, possibly involving external shocks as the jet interacts with its environment, but in some cases it overlaps with the prompt phase, blurring the distinction. Theoretical tensions arise because no single mechanism explains all observed features cleanly. Synchrotron emission struggles with spectral slopes but explains variability well. Photospheric emission explains efficiency and peak energies but struggles with complexity. Inverse Compton processes explain high-energy photons but depend sensitively on poorly known conditions. Hybrid models can fit data, but at the cost of increased parameter freedom, making it difficult to draw firm physical conclusions. This situation is not a failure of theory so much as a reflection of the extreme regime being studied. Gamma-ray bursts operate at the intersection of relativistic fluid dynamics, plasma physics, radiation transport, and strong gravity. Each of these fields is challenging on its own. Combined, they produce behavior that resists simple explanation. Importantly, the prompt emission region is not directly observable in space. It cannot be imaged. Its size, shape, and internal structure must be inferred indirectly through timing, spectra, and statistical patterns. Small uncertainties in assumptions can propagate into large differences in interpretation. What is clear is that the gamma rays are not a trivial byproduct. They are the primary channel through which the jet releases energy during the burst. They are produced under conditions where particles are accelerated to extreme energies on microscopic timescales, where magnetic fields are dynamically important, and where relativistic effects dominate every observable. The unresolved tensions in prompt emission physics are not signs of stagnation. They are signs that the field has reached a level of precision where simple models are no longer sufficient. As detectors improve and time-resolved spectroscopy becomes more detailed, constraints tighten. Some ideas are ruled out, others are refined. Future observations, especially those combining gamma rays with neutrinos, gravitational waves, and polarization measurements, may finally distinguish between competing models. They may reveal whether most gamma-ray bursts are shock-powered, magnetically powered, photosphere-dominated, or some evolving combination of all three. For now, the prompt emission remains the most direct and most enigmatic window into the heart of gamma-ray bursts. It is the moment when invisible engines announce themselves through pure radiation, converting gravity, motion, and magnetic stress into the brightest flashes the universe can produce. The gamma rays fade quickly, but the event is far from over. What follows a gamma-ray burst is not an echo in the usual sense, but a second, longer-lived phase of radiation that unfolds across the electromagnetic spectrum. This is the afterglow. It can last days, weeks, sometimes months, and it transforms a fleeting flash into a measurable astrophysical object, one that can be localized, dissected, and understood in physical detail. The afterglow is produced when the relativistic jet, which carried the energy outward during the prompt phase, begins to interact with its surroundings. Until this point, the jet has been largely isolated, expanding freely through near vacuum. Eventually, it encounters the interstellar medium of its host galaxy. Diffuse gas, dust, and magnetic fields spread thinly between stars. That encounter changes everything. As the jet plows into this external material, it begins to decelerate. A shock forms at the interface between the jet and the ambient medium. This is known as the external forward shock. At the same time, a reverse shock can propagate backward into the jet itself. These shocks heat particles, amplify magnetic fields, and accelerate electrons to relativistic energies. The result is broadband radiation, spanning from X-rays down to radio waves. Unlike the prompt emission, which is highly variable and difficult to localize precisely, afterglows evolve smoothly. Their brightness typically decays as a power law in time, fast at first, then more slowly. This predictable behavior is one of the great successes of gamma-ray burst theory. It allows the physics of the jet-environment interaction to be modeled with a degree of confidence that is rare in high-energy astrophysics. X-ray afterglows are usually the first to be detected. Space-based observatories can slew rapidly to the burst position, often within minutes. In X-rays, the afterglow may be extraordinarily bright initially, sometimes rivaling persistent cosmic X-ray sources before fading steadily. X-ray light curves often show breaks, changes in decay rate, that encode information about jet geometry and energy injection. Optical afterglows were the crucial breakthrough that turned gamma-ray bursts from mysterious flashes into cosmological probes. When optical telescopes first detected fading points of light at burst locations, it became possible to measure redshifts using spectroscopy. Absorption lines imprinted by gas in the host galaxy or along the line of sight provided direct distance measurements. Those distances were staggering. Many bursts were located billions of light years away. Some originated when the universe was less than a tenth of its current age. The immense energies inferred from those distances confirmed that gamma-ray bursts were not local phenomena, but among the most powerful events in cosmic history. Infrared afterglows extend this reach even further. At high redshift, optical light is redshifted into the infrared, making infrared observations essential for studying the earliest bursts. Infrared data are also less affected by dust extinction, allowing afterglows hidden in dusty, star-forming regions to be detected. Radio afterglows appear later, sometimes days or weeks after the burst. They are faint but long-lived. Radio emission arises from the same population of shock-accelerated electrons, but at lower characteristic energies. Because radio waves interact weakly with intervening material, radio afterglows provide a clean probe of the total energy and geometry of the outflow long after the initial explosion. Across all these wavelengths, the underlying physics is remarkably unified. The standard afterglow model assumes that electrons accelerated in the external shock follow a power law energy distribution. A fraction of the shock energy goes into accelerating these electrons. Another fraction goes into amplifying magnetic fields. The electrons then emit synchrotron radiation as they spiral through those fields. From this framework, a characteristic spectrum emerges, defined by several break frequencies. One corresponds to the minimum energy of the accelerated electrons. Another corresponds to the cooling frequency, where radiative losses become important. A third marks the self-absorption frequency at which the plasma becomes opaque to its own radiation. The relative positions of these frequencies determine how the afterglow appears at different wavelengths and times. As the shock slows and expands, these frequencies shift downward. X-ray emission fades first, optical emission follows, radio emission persists the longest. This ordered evolution is not incidental. It is a direct consequence of relativistic shock physics and synchrotron radiation. Afterglows do more than confirm distances. They reveal the environments in which gamma-ray bursts occur. The density of the surrounding medium affects how quickly the jet decelerates and how bright the afterglow becomes. Long bursts often show afterglow signatures consistent with dense, wind-shaped environments produced by massive stars shedding material before collapse. In these cases, the density decreases with distance from the progenitor, leaving an imprint on the afterglow's temporal evolution. Short bursts more often show afterglows consistent with low-density, uniform media. This fits with their occurrence in older galaxies or far from star-forming regions. The faintness of many short-burst afterglows is not merely an observational inconvenience, it is a physical clue pointing to their origin in sparse environments. Afterglows also reveal jet geometry. One of the most important features in an afterglow light curve is the jet break. Early on, the relativistic beaming of the jet confines visible emission to a narrow cone. As the jet slows, its beaming angle widens. Eventually, the edge of the jet becomes visible. At this point, the light curve steepens, producing a break that is achromatic. It appears at all wavelengths at roughly the same time. The timing of this jet break allows the jet's opening angle to be estimated. This, in turn, allows the true energy of the burst to be calculated by correcting for beaming. These corrections dramatically reduce the energy budget compared to isotropic estimates, bringing them into alignment with plausible central engines. Not all afterglows show clear jet breaks. In some cases, the break occurs too late to observe. In others, structured jets, where energy varies smoothly with angle rather than cutting off sharply, produce more gradual transitions. The diversity of afterglow behavior has led to increasingly nuanced models of jet structure. Afterglows can also show additional features. Some display flares in X-rays minutes to hours after the burst, suggesting renewed activity from the central engine or late-time energy injection into the jet. Others show plateaus, periods of nearly constant brightness, before resuming their decline. These features challenge the simplest external shock models and hint at complex engine behavior, even after the prompt phase. In rare cases, afterglows reveal more dramatic surprises. A sudden rebrightening may occur when the jet encounters a denser region of the interstellar medium. Polarization measurements can reveal the geometry and coherence of magnetic fields. Spectroscopy can detect absorption from intervening gas clouds, providing information about the intergalactic medium across cosmic time. For long bursts, afterglows sometimes give way to an additional component, the emerging supernova. Days to weeks after the burst, the optical light curve may flatten and then brighten again as the supernova becomes visible. This connection, established through afterglow observations, cemented the link between long gamma-ray bursts and the deaths of massive stars. For short bursts, afterglows played a key role in identifying kilonovae, transient optical and infrared emission powered by the radioactive decay of heavy elements formed in neutron star mergers. These signals are fainter and faster than supernovae, but their detection confirmed theoretical predictions and tied short bursts to our process nucleosynthesis. From a methodological perspective, afterglows are what make gamma-ray burst science possible. The prompt emission announces the event, but the afterglow allows it to be studied. Without afterglows, distances would remain uncertain, host galaxies unidentified, and physical models weakly constrained. There is a deeper significance as well. Afterglows demonstrate that gamma-ray bursts are not isolated flashes disconnected from their environments. They are interactions, violent but intelligible, between relativistic matter and the ordinary material that fills galaxies. The fading light is a record of that interaction, written across the spectrum and stretched over time. Each afterglow is a controlled experiment conducted by the universe itself. The initial conditions vary, but the governing physics remains the same. By comparing many afterglows, patterns emerge. By modelling individual ones in detail, specific systems can be reconstructed. Together, they turn momentary brilliance into enduring knowledge. The gamma rays tell us that something extraordinary has happened. The afterglow tells us where, how, and in what kind of universe it occurred. Gamma ray bursts do not merely occur in the universe. They cut through it. Because they are so luminous and so brief, they act like cosmic flares, momentary beacons that illuminate regions of space and time that would otherwise remain inaccessible. Long before astronomers could observe ordinary galaxies at extreme distances, gamma-ray bursts were already announcing themselves from the deep past, arriving with energies so concentrated that even the young, dim universe could not hide them. This is what gives gamma-ray bursts their extraordinary cosmological reach. To understand why, it helps to think about how most astronomical objects fade with distance. Galaxies shine because they contain billions of stars. As distance increases, their light spreads out and their surface brightness diminishes. Eventually, even the largest galaxies become too faint to detect. This limitation becomes severe in the early universe, where galaxies are small, metal-poor, and intrinsically dim. Gamma-ray bursts do not suffer from this problem in the same way. A burst concentrates an enormous amount of energy into seconds and beams it into a narrow jet. The apparent brightness does not scale like a galaxy's diffuse glow. Instead, it behaves like a flashbulb visible across cosmic expanses. A gamma-ray burst occurring at a redshift of 10 when the universe was less than 500 million years old can still outshine every galaxy around it, if only briefly. This is not hypothetical. Such bursts have been observed. High redshift gamma-ray bursts are among the most distant individual events ever detected. Some originate from epochs when the first generations of stars were still forming, when the intergalactic medium was undergoing profound transformation. The fact that we can see them at all is a direct consequence of their extreme luminosity and their gamma-ray emission, which is largely immune to dust extinction. Gamma rays pass through dust and gas that would completely obscure optical light. Even when the prompt emission is redshifted into lower energy bands, it remains detectable by space-based instruments. The afterglow, too, often persists long enough to be studied in infrared wavelengths, where absorption is weaker. Together, these properties allow gamma-ray bursts to act as probes of the early universe in ways that no other transient phenomenon can. One of the first insights gained from high redshift bursts concerned the history of star formation. Long gamma-ray bursts are linked to the deaths of massive stars. Massive stars form quickly and die young. This means that the rate of long bursts closely tracks the rate of massive star formation. By measuring how frequently bursts occur at different redshifts, astronomers can infer how star formation evolved over cosmic time. This method is complementary to traditional galaxy surveys. Galaxy surveys are biased toward brighter, more massive systems. Gamma-ray bursts, by contrast, can originate in faint, low-mass galaxies that would otherwise go undetected. In fact, many high redshift bursts are associated with host galaxies that are too dim to observe directly, even with powerful telescopes. This makes gamma-ray bursts uniquely sensitive to star formation in small, primitive galaxies, the kind that dominated the early universe. When burst rates are corrected for observational biases, they suggest that star formation in the early universe may have been more widespread than galaxy surveys alone imply. Small, metal-poor galaxies forming massive stars could contribute significantly to the total star formation budget, even if they remain invisible as extended objects. Metallicity plays a role here as well. Long gamma-ray bursts preferentially occur in low metallicity environments. In the early universe, metals were scarce. This naturally enhances the burst rate per unit star formation at high redshift. As a result, gamma-ray bursts are not just passive tracers of star formation, they are biased tracers, weighted toward the conditions that prevailed in the cosmic dawn. That bias, once understood, becomes a feature rather than a flaw. It allows bursts to highlight exactly the environments that are otherwise hardest to study. Gamma-ray bursts also probe one of the most important transitions in cosmic history: rhionization. After the universe cooled enough for protons and electrons to combine, it entered a long period known as the Cosmic Dark Ages. Neutral hydrogen filled space, absorbing ultraviolet light and preventing it from travelling far. Eventually, the first stars and galaxies formed and began emitting energetic radiation. That radiation rhionized the hydrogen, transforming the intergalactic medium from opaque to transparent. Pinning down when and how this rhionization occurred is one of the central challenges of modern cosmology. Gamma-ray burst afterglows offer a powerful tool for addressing this problem. As the afterglow light travels toward Earth, it passes through intergalactic hydrogen. Neutral hydrogen absorbs light at specific wavelengths, producing characteristic absorption features in the spectrum. The most prominent of these is the Lyman alpha absorption edge. By studying how this absorption changes with redshift, astronomers can infer the fraction of hydrogen that was neutral at different epochs. A sharp absorption cutoff indicates a highly neutral medium. A smoother profile suggests partial ionization. Unlike quasars, which are persistent and can ionize their surroundings, gamma-ray bursts are brief. They do not significantly alter the ionization state of the intergalactic medium along their line of sight. This makes them cleaner probes of the ambient conditions in the early universe. In high redshift bursts, afterglow spectra have revealed substantial neutral hydrogen fractions, consistent with a universe still in the process of rhionization. Each such observation adds a data point to the timeline of cosmic transformation, helping to constrain when the first luminous structures reshaped their surroundings. Gamma-ray bursts also illuminate the chemical evolution of the universe. As afterglow light passes through gas clouds in the host galaxy and along the line of sight, it picks up absorption lines from elements such as carbon, oxygen, silicon, and iron. The strength and pattern of these lines reveal the metallicity of the gas, the abundance of elements heavier than helium. In the early universe, metallicity was low. The first generations of stars synthesized heavy elements and dispersed them into their surroundings through supernova explosions. By measuring metallicities in burst-host galaxies at different redshifts, astronomers can trace how chemical enrichment progressed over time. These measurements show that even at very high redshift, some galaxies had already undergone significant chemical evolution, others remained extremely metal-poor. Gamma-ray bursts sample both populations, offering a more complete picture of early galactic diversity than surveys biased toward luminous systems. The reason bursts are visible from the cosmic dawn is ultimately physical rather than technological. The engines that produce gamma-ray bursts, collapsing massive stars and compact object mergers, do not require a mature universe. They require gravity, rotation, and nuclear matter. Massive stars can form as soon as gas clouds become dense enough to collapse, even in environments lacking heavy elements. In fact, low metallicity may make it easier for stars to retain the angular momentum needed to produce a burst. Once formed, these stars die quickly. There is little delay between star formation and burst production. This allows gamma-ray bursts to trace the earliest episodes of stellar activity almost in real time on cosmological scales. The radiation they produce is ideally suited for long-distance travel. Gamma rays are unaffected by dust. Relativistic beaming boosts their apparent brightness. Time dilation stretches their duration, making them easier to detect. A burst that lasts a few seconds in its own frame may last tens of seconds when observed from Earth at high redshift. This combination, intrinsic luminosity, favourable beaming, and relativistic effects, makes gamma-ray bursts the most distant electromagnetic signals routinely observed. There is also a philosophical shift that comes with this realization. When astronomers look at distant galaxies, they are studying structures that have persisted for millions or billions of years. When they observe a gamma ray burst from the same epoch, they are witnessing an instant. A single stellar death occurring in a tiny region of space becomes visible across the universe. This changes how we think about observability in cosmology. It shows that understanding the early universe does not require seeing everything all the time. Sometimes, a single, well-placed flash can reveal more than a deep, static image. Gamma-ray bursts do not replace other cosmological probes. They complement them. They fill in gaps where galaxies are too faint, quasars too rare, or backgrounds too smooth. They provide line-of-sight information with exquisite sensitivity, tied directly to the life cycle of stars. As instruments improve and more high redshift bursts are detected, their role as cosmological tools will only grow. Each burst adds another thread connecting the local physics of extreme objects to the global history of the universe. In that sense, gamma-ray bursts are not just the brightest moments in the universe, they are among the most informative. Gamma-ray bursts sit at the edge of what physics allows, but not beyond it. Their defining feature is not that they violate known laws, but that they operate so close to fundamental limits that every inefficiency, every stray particle, and every geometric detail matters. They are events where gravity, relativity, nuclear physics, and plasma dynamics all press simultaneously against their maximum tolerances. The sense of extremity begins with energy budgets. When astronomers first estimated the energies of gamma-ray bursts under the assumption of isotropic emission, the numbers were unsettling. Some bursts appeared to release more than 10 to the 54 ergs of energy in gamma rays alone. This is comparable to converting the mass of the Sun directly into energy via Einstein's mass-energy equivalence. To do that in a few seconds would require a power output exceeding anything previously known in astrophysics. Those early estimates were not wrong in calculation, but they were wrong in interpretation. The key correction came from beaming. Once the emission was understood to be confined to narrow jets, the true energy requirements dropped dramatically. Typical beaming-corrected energies cluster around 10 to the 51 ergs, sometimes lower, sometimes higher, but rarely exceeding a few times 10 to the 52 ergs. Even these reduced numbers remain extraordinary. To put them in context, consider rest mass energy. The mass of the Sun corresponds to roughly 2 times 10 to the 54 ergs. A gamma-ray burst releasing 10 to the 51 ergs in radiation has converted about 1,000th of a solar mass directly into energy. That may sound small, but it is an enormous fraction by astrophysical standards. Ordinary nuclear fusion converts less than 1% of mass into energy over billions of years. Gamma-ray bursts achieve comparable efficiency in seconds. The central engines that power bursts make this possible by exploiting gravitational energy rather than nuclear energy. When matter falls deep into a gravitational potential well, such as that of a black hole or a neutron star, a significant fraction of its rest mass energy can, in principle, be liberated. For accretion onto a black hole, efficiencies of up to 10% are possible, and even higher if the black hole is rapidly spinning. This sets an upper bound. If a gamma-ray burst engine accretes a few tenths of a solar mass, converting a few percent of that mass into energy, the resulting budget naturally falls in the observed range. No new physics is required. What is required is that the energy be extracted cleanly and directed efficiently. Efficiency is therefore a central constraint. A gamma-ray burst is not merely an energetic event, it is an efficient one. A large fraction of the energy available in the central engine must be converted into relativistic outflow, and a substantial fraction of that outflow energy must then be converted into radiation. Inefficiencies compound quickly. If too much energy is lost to heating, turbulence, or uncollimated motion, the observed burst would be far dimmer than it is. This is one reason why internal shock models have faced scrutiny. Internal shocks convert only a modest fraction of kinetic energy into radiation. If the jet consists of shells with similar speeds, collisions are weak and inefficient. To compensate, the total energy budget would need to be larger, pushing against physical limits. Magnetically dominated models address this by storing energy in ordered magnetic fields rather than in bulk motion. Magnetic reconnection can release energy directly into particle acceleration and radiation with higher efficiency. Photospheric models similarly exploit the fact that thermal energy trapped in an opaque flow can later be released efficiently once transparency is reached. Observations suggest that gamma-ray bursts are operating close to the upper envelope of what efficient energy conversion allows, but not beyond it. The fact that their inferred energies cluster rather than diverge wildly is itself informative. It suggests that the engines self-regulate, limited by fundamental constraints rather than arbitrary initial conditions. One of the most severe of those constraints is baryon loading. Baryons, protons and neutrons, are heavy. To accelerate matter to Lorentz factors of hundreds, the amount of baryonic mass in the jet must be extremely small. If too many baryons are present, the available energy is spread over too much mass, and the outflow cannot reach the required speeds. The gamma rays would be trapped, softened, or never produced at all. This creates a paradox. Gamma-ray bursts originate in environments rich in baryons. Collapses occur inside stars. Neutron star mergers eject dense nuclear matter. How then does a jet emerge that is clean enough, baryon-poor enough, to achieve ultrarelativistic motion? This is known as the baryon loading problem. The solution lies in geometry, timing, and magnetic fields. Jets form along rotation axes where matter density is lowest. In collapses, the polar regions of the star may be relatively evacuated by rotation and earlier mass loss. In mergers, tidal debris tends to concentrate in the equatorial plane, leaving polar funnels through which jets can escape. Magnetic fields play a crucial role as well. Magnetically driven jets can accelerate plasma while excluding baryons, effectively filtering the outflow. Pair plasmas of electrons and positrons can be accelerated more easily than baryonic matter. If the jet is launched magnetically and remains magnetically dominated, baryon contamination can be minimized. Still, the margin is narrow. Adding as little as a 10,000th of a solar mass of baryons to the jet would drastically reduce the attainable Lorentz factor. Gamma-ray bursts therefore represent finely tuned flows that thread their way through hostile environments without being poisoned by excess mass. Another limiting factor is opacity. At the energies involved, gamma rays can annihilate each other to produce electron-positron pairs. This process becomes significant if photons are too dense or too isotropic. Without relativistic motion, the emission region would become opaque, and the radiation would thermalize rather than escape as gamma rays. The observed non-thermal spectra require that the emission occur in regions that are optically thin. This sets a minimum Lorentz factor for the jet. Observations of very high-energy photons, tens of gigaelectron-volts in some bursts, push this minimum even higher. In some cases, Lorentz factors of several hundred are required simply to allow the photons to escape. These constraints link microphysics to global energetics. The jet must be fast enough, clean enough, and ordered enough for radiation to emerge without self-destruction. That such conditions are achieved at all is a testament to the robustness of the underlying mechanisms. Gamma-ray bursts also approach limits set by radiation pressure. When luminosities become extremely high, radiation itself exerts force. In ordinary stars, radiation pressure counteracts gravity and shapes stellar structure. In gamma-ray bursts, radiation pressure can dominate the dynamics of the outflow. Photons carry momentum, and at these intensities, that momentum is not negligible. This pressure can accelerate particles, shape shocks, and influence jet stability. It also imposes constraints on how energy is deposited. If radiation is released too deep in the flow, it can choke the jet or alter its composition. Successful bursts must release their radiation in regions where the balance between matter, magnetic fields, and photons permits escape. Despite all these extremes, gamma-ray bursts do not violate known physical laws. They do not exceed the speed of light. They do not require exotic forms of energy. They do not circumvent conservation principles. Every aspect of their behavior can, in principle, be derived from general relativity, electrodynamics, nuclear physics, and statistical mechanics. What makes them challenging is not that the laws fail, but that the conditions push those laws into regimes rarely encountered. They are natural experiments in relativistic plasma physics. Consider acceleration. The fastest particle accelerators on Earth push protons to energies of tera-electron volts. Gamma-ray bursts accelerate particles to energies orders of magnitude higher. Magnetic fields, shocks, and turbulence operate at intensities impossible to replicate in laboratories. Yet the same equations govern both regimes. Consider gravity. Black hole formation and neutron star mergers involve space-time curvature strong enough to produce measurable gravitational waves, yet those waves propagate exactly as predicted by general relativity, even when generated by events releasing enormous energy in milliseconds. The fact that gamma-ray bursts obey known laws is itself a powerful confirmation of those laws. Each burst is a stress test. Every detected photon and every measured timescale constrains how far physics can be pushed without breaking. There is also an important selection effect to remember. We observe only the most successful gamma-ray bursts. Many engines likely fail. Jets may stall inside stars. Baryon loading may be too high. Accretion may shut off too quickly. These events would produce weak or no gamma-ray emission and would go unnoticed. The bursts we see are the survivors, the ones that navigated the narrow corridor of physical possibility. This biases our view toward the upper extremes of efficiency and collimation. Understanding gamma-ray bursts therefore requires acknowledging not just what happens, but what almost happened and failed. From a cosmological perspective, the energy released by gamma-ray bursts does not dominate the universe. They are rare, Their total contribution to cosmic energy budgets is negligible compared to starlight or cosmic background radiation. Their importance lies not in their cumulative effect, but in their intensity and clarity. They reveal what is possible. Gamma-ray bursts show that gravity can organize matter and energy into configurations that release astonishing power without chaos. They show that relativistic flows can remain coherent across vast distances. They show that magnetic fields can channel energy with extraordinary precision. They show that known physics, when pushed to extremes, is more capable than intuition suggests. In that sense, gamma-ray bursts occupy a special place in astrophysics. They are not anomalies that demand new laws. They are confirmations of existing ones, operating at their outer edges. The universe is not breaking its own rules when it produces a gamma-ray burst. It is demonstrating just how far those rules can be taken. For most of their history, gamma-ray bursts were solitary messengers. They arrived as flashes of light, extraordinarily bright, richly structured and deeply informative, but fundamentally isolated. From a single channel of information, astronomers inferred engines, distances, and energies. The picture was compelling, but incomplete. Too much had to be reconstructed indirectly. Too many assumptions sat between observation and physical certainty. That changed when the universe spoke in more than one voice at once. The multi-messenger breakthrough did not begin with gamma rays. It began with space-time itself. Gravitational waves are ripples in the fabric of space-time produced by accelerating masses. They were predicted by general relativity a century before they were detected, and for decades they remained a theoretical curiosity. The distortions they produce are minuscule, changes in length smaller than the diameter of a proton over kilometers of distance. Detecting them required instruments of unprecedented sensitivity and stability. When gravitational wave detectors finally reached that sensitivity, they opened an entirely new observational window. For the first time, astronomers could observe motion and mass directly, rather than inferring them from light. Compact object mergers were always expected to be among the strongest sources of gravitational waves. Binary neutron stars, in particular, are nearly ideal emitters. As they orbit, they lose energy efficiently, producing a clean, predictable signal that sweeps upward in frequency as the end spiral accelerates. For years, theorists had argued that these same mergers should also produce short gamma-ray bursts. The reasoning was solid. The merger creates a compact remnant and an accretion disk. Jets form. Gamma rays are emitted. But until the two signals were observed together, the connection remained circumstantial. The decisive moment came when a gravitational wave signal from a binary neutron-star merger was detected, and a gamma-ray burst followed almost immediately. The timing mattered. The gamma rays arrived less than 2 seconds after the gravitational wave signal reached its peak. This delay was short enough to rule out many alternative explanations and long enough to provide constraints on jet formation and propagation. The two signals came from the same region of the sky. The coincidence was overwhelming. For the first time, a gamma-ray burst was no longer just a flash of light. It was a space-time event. This joint detection resolved long-standing debates in one stroke. Short gamma-ray bursts were confirmed as products of compact object mergers. Gravitational waves were confirmed to travel at essentially the speed of light. The central engines inferred from electromagnetic data were anchored to directly measured masses and orbital dynamics. But the story did not stop with gamma rays and gravitational waves. Within hours, telescopes across the world turned toward the merger's location. What they saw was something new. In optical and infrared light, a transient source appeared and evolved rapidly. It brightened, changed colour, and faded on timescales of days. Its spectrum did not resemble a supernova. It was too fast, too red, and too faint at peak brightness. This was the long-predicted but never-before-observed kilonova. A kilonova is powered not by shock-heated gas or radioactive nickel, as in supernovae, but by the radioactive decay of freshly synthesized heavy nuclei. During a neutron-star merger, some fraction of neutron-rich matter is ejected at high speed. In that ejector, conditions are ideal for rapid neutron capture, the R process. The R process is responsible for creating roughly half of all elements heavier than iron. It requires environments with extreme neutron densities, where atomic nuclei can capture neutrons faster than they can decay. For decades, astrophysicists debated where such conditions exist. Supernovae were candidates, but detailed models struggled to produce the necessary abundances. Neutron star mergers, by contrast, provide exactly the right conditions. The kilonova light curve is powered by the decay of R process nuclei. As these unstable elements decay towards stability, they release energy that heats the ejector, producing thermal emission. The opacity of this material is high, especially when it contains lanthanides and actinides. This causes the emission to peak in the infrared and to evolve rapidly. Observations matched these predictions with striking precision. The color evolution revealed multiple ejector components. A fast, relatively light component produced early, bluer emission. A slower, heavier component rich in lanthanides produced redder emission later. The inferred masses of the ejector were sufficient to account for a significant fraction of the universe's heavy element inventory. This was not merely suggestive. It was quantitative. From a single event, astronomers could estimate how much gold, platinum, and other heavy elements were produced. The numbers were astonishing. The merger synthesized amounts of precious metals comparable to the mass of the Earth. Spread over cosmic time and many such events, neutron star mergers could plausibly account for most of the universe's supply of these elements. Gamma-ray bursts in this context are not just energetic beacons, they are signposts of cosmic alchemy. The short gamma-ray burst marks the moment when a relativistic jet successfully escapes. The gravitational waves reveal the in-spiral and merger dynamics. The kilonova reveals the synthesis of heavy elements. Together, these signals form a complete narrative linking space-time dynamics, high-energy astrophysics, nuclear physics, and chemical evolution. This convergence transformed short gamma-ray bursts from speculative phenomena into central players in a unified physical picture. It also reshaped how astrophysics is done. Before multi-messenger observations, many parameters had to be inferred indirectly. Jet angles were estimated from afterglows, masses were guessed from models, energies were bounded by assumptions. With gravitational waves, masses and orbital parameters are measured directly. With electromagnetic counterparts, geometry and energetics are constrained independently. This redundancy is powerful. It allows cross-checks that were previously impossible. It exposes hidden biases. It forces theoretical models to satisfy multiple independent datasets simultaneously. Multi-messenger observations also revealed subtleties that would have been invisible in a single channel. For example, the observed gamma-ray burst associated with the neutron star merger was unusually weak. On its own, it might have been classified as atypical. Combined with afterglow observations and gravitational wave data, it became clear why. The jet was not pointed directly at Earth. We were viewing it off-axis. As the jet slowed and spread, its afterglow brightened gradually, producing a delayed rise in X-ray and radio emission. This behavior matched models of structured jets, where energy is distributed smoothly with angle rather than confined to a sharp-edged cone. Such models had been discussed for years. Multi-messenger data made them testable. The implications extend beyond a single event. If short gamma-ray bursts are associated with neutron star mergers, then the rate of detected bursts can be linked to the merger rate inferred from gravitational waves. This connection helps correct for beaming and observational biases. It allows estimates of how many mergers go unseen electromagnetically and how many bursts are missed due to unfavorable orientation. Conversely, gamma-ray bursts can alert astronomers to mergers that gravitational wave detectors may miss, especially at higher redshifts where sensitivity drops. Together, the two messengers extend each other's reach. There is also a deeper implication for cosmic history. Heavy elements are not produced uniformly. They are forged in rare extreme events and then dispersed into galaxies over long timescales. The fact that neutron star mergers can produce vast quantities of R-process elements means that the chemical evolution of galaxies is punctuated by rare but decisive episodes. Planets, life, and technology depend on elements like iron, gold, iodine, and uranium. Their presence in the universe is tied to violent events that briefly release enormous energy and then fade. Gamma-ray bursts are part of that chain. They are not just signals of destruction, but of creation. This perspective changes how bursts are framed. They are no longer just the brightest moments in the universe. They are moments when the universe reshapes its own composition. When space-time rings, matter collides, and the periodic table grows heavier. Multi-messenger astronomy is still young. Only a handful of such joint detections exist so far. But even this small sample has already validated decades of theoretical work and revealed new layers of complexity. Future detections will extend this picture. More mergers will be observed. Variations will emerge. Some events will produce strong gamma-ray bursts. Others will not. Some will eject large amounts of neutron-rich material. Others will collapse quietly into black holes. Each case will refine the role gamma-ray bursts play in the cosmic ecosystem. What was once a solitary flash is now understood as one strand in a tightly woven physical process. Light, gravity, and matter all carry parts of the same story, and for the first time we are hearing them together. Gamma-ray bursts are not discovered by chance anymore. They are caught by machines designed to react faster than any human ever could, to signals that last less than a heartbeat, and arrive without warning from any direction in the sky. Detecting an event that may last only a few tens of milliseconds, emit photons too energetic for lenses or mirrors, and originate billions of light years away requires a very particular kind of observatory. Gamma-ray burst astronomy is therefore inseparable from its technology. What we know about bursts is shaped directly by how we detect them. The first challenge is simple to state and difficult to solve. Gamma rays cannot be focused. At optical wavelengths, telescopes collect light with mirrors or lenses and form images. X-ray telescopes can focus photons using grazing incidence optics. Gamma rays are too energetic for either approach. They pass through most materials or interact violently, producing particle cascades rather than clean reflections. As a result, gamma-ray detectors work fundamentally differently from traditional telescopes. Instead of forming images, they count interactions. Most gamma-ray burst detectors use scintillators or semiconductor materials. When a gamma-ray photon enters the detector, it interacts with the material through processes like photoelectric absorption, Compton scattering, or pair production. These interactions produce charged particles, which in turn generate flashes of light or electrical signals. Those signals are recorded with precise timing. What matters most is not where the photon came from, but when it arrived and how much energy it deposited. This emphasis on timing and energy shapes every aspect of burst detection. Instruments are built to monitor large fractions of the sky continuously, watching for sudden increases in gamma-ray count rates. When a statistically significant spike appears, the system triggers. A trigger is the defining moment of a gamma-ray burst observation. Trigger algorithms run continuously on board satellites. They compare incoming photon counts over multiple timescales, milliseconds, seconds, tens of seconds, to background levels. If the count rate rises sharply above background in a way consistent with a burst, the instrument declares a trigger. This must happen autonomously. There is no time to consult Earth. By the time a signal could travel down, be analysed and return, the burst would be over. Trigger criteria are carefully tuned. If they are too sensitive, the instrument will trigger constantly on noise, cosmic rays, or solar activity. If they are too conservative, real bursts will be missed. Modern systems use multiple energy bands and timescales simultaneously to distinguish genuine astrophysical events from spurious ones. Once a trigger occurs, the instrument changes mode. Data that might normally be compressed or discarded are preserved. Time resolution is increased. Energy channels are refined. In effect, the detector shifts into a high-priority state, capturing as much information as possible during the brief window when the burst is active. But detection alone is not enough. Localization is the next hurdle. Because gamma rays cannot be focused easily, determining where a burst came from is non-trivial. Early detectors could only say that a burst came from somewhere within a large patch of sky, sometimes spanning tens of degrees. That was sufficient to prove bursts were cosmic, but not to identify counterparts. Modern localization relies on several techniques. One method uses relative count rates across multiple detectors oriented in different directions. If a burst arrives from one side of a spacecraft, detectors facing that direction will register higher counts than those facing away. By comparing these rates, a rough position can be inferred. Another method involves coded masks. In this approach, a patterned mask sits above a position-sensitive detector. Gamma rays passing through the mask cast a shadow pattern on the detector that depends on the direction of arrival. By decoding that pattern, the burst location can be reconstructed with much higher precision, sometimes to arc-minute scales. A third method uses triangulation between multiple spacecraft. If detectors on widely separated satellites record the same burst, the differences in arrival times constrain the direction. This technique was crucial in early gamma-ray burst astronomy and remains valuable today, especially for very bright events. Localization accuracy matters because it determines what happens next. Gamma-ray bursts are fleeting. If follow-up observations do not begin quickly, critical information is lost. Afterglows fade rapidly, especially at higher energies. The ability to localize a burst precisely and transmit that information to the ground within seconds is one of the defining achievements of modern burst observatories. Once a burst is localized, a second network activates rapid follow-up. Automated alerts are sent to observatories around the world within seconds of detection. These alerts include the burst time, position, estimated uncertainty, and basic properties like duration and brightness. Robotic telescopes can respond immediately, slewing to the burst location without human intervention. This speed is essential. Optical afterglows can fade by orders of magnitude in minutes. X-ray afterglows evolve on similar timescales. Infrared observations are particularly time-sensitive for high redshift bursts. The difference between observing within 1 minute versus 10 can be the difference between a rich dataset and a non-detection. Modern gamma-ray burst astronomy is therefore an exercise in coordination. Space-based detectors act as sentinels, watching the sky continuously. When they trigger, they hand off the event to a global network of ground-based telescopes and other space missions. Each instrument contributes a piece of the puzzle, covering different wavelengths and timescales. Detector physics underpins all of this. Gamma-ray burst detectors must handle enormous dynamic ranges. A burst may be barely detectable above background, or it may be so bright that it threatens to saturate the detector. Electronics must respond linearly across many orders of magnitude. Dead time, the brief interval after each detection during which the detector cannot record another event, must be minimized and carefully calibrated. Energy resolution is another challenge. While gamma-ray burst spectra are broad, subtle features matter, measuring the peak energy accurately requires detectors that can distinguish between photons differing by tens of kilo-electron volts. This demands careful calibration and stable operating conditions. Timing resolution is equally critical. Millisecond variability carries information about source size and emission mechanisms. Detectors must timestamp events with microsecond precision and maintain clock synchronization over long periods. Background rejection is a constant concern. Space is filled with charged particles from cosmic rays and the sun. These can produce signals that mimic gamma-ray interactions. Detectors use shielding, anti-coincidence systems, and pattern recognition to distinguish genuine gamma rays from charged particle events. Orbit matters as well. Low Earth orbit exposes detectors to trapped radiation belts and Earth albedo gamma rays. Higher orbits reduce some backgrounds but introduce others. Instrument design is always a compromise between sensitivity, stability, and operational constraints. One of the most important advances in burst detection has been rapid onboard localization, coupled with autonomous spacecraft slewing. Some satellites are capable of reorienting themselves within tens of seconds to point narrow-field instruments directly at the burst location. This allows X-ray and optical observations to begin while the afterglow is still bright, sometimes even overlapping with the tail end of the prompt emission. This capability transformed the field. It turned gamma-ray bursts from transient alerts into multi-wavelength events observed from their earliest moments. It enabled redshift measurements, host galaxy identification, and detailed afterglow modeling. Detection technology also shapes what kinds of bursts we see. Instrument sensitivity varies with energy. Some detectors are optimized for lower energy gamma rays and X-rays, making them more sensitive to softer bursts and X-ray flashes. Others emphasize higher energies, capturing hard, short bursts more effectively. The observed population is therefore filtered by detector design. Time resolution and trigger thresholds influence which bursts are detected. Extremely short bursts may be missed if trigger windows are too long. Very faint bursts may be lost in background noise. Understanding these selection effects is essential for interpreting burst statistics and rates. As detection technology has improved, new classes of events have emerged. Ultra-long bursts lasting thousands of seconds, low luminosity bursts associated with nearby supernovae, short bursts with extended emission. Each new detection regime challenges existing models and expands the taxonomy of gamma-ray bursts. Modern observatories also operate in a multi-messenger context. Gravitational wave detectors provide independent triggers for compact object mergers. Neutrino observatories search for coincident signals from the same events. When a gamma-ray burst trigger coincides with a gravitational wave detection, the urgency and precision of follow-up increase dramatically. This integration places new demands on detection technology. Localization must be faster and more accurate. Communication networks must be robust. Data pipelines must handle real-time analysis across observatories that were once separate disciplines. Catching events that last fractions of a second requires not just sensitive detectors, but a philosophy of observation that prioritizes readiness over deliberation. Gamma-ray burst observatories do not wait for targets, they wait for surprises. They stare at empty sky, recording nothing of interest for hours or days, and then, without warning, they become the most important instruments in astrophysics for a few seconds. Their success is measured not by how often they detect bursts, but by how well they respond when they do. In this sense, gamma-ray burst detection is as much about engineering as it is about astronomy. It is about building systems that can recognize significance instantly, preserve fragile information, and distribute it globally before the universe moves on. The flashes themselves are brief. The infrastructure built to catch them is permanent. And because of that infrastructure, events lasting less than a second can reshape our understanding of the cosmos. The more gamma-ray bursts have been observed, the more sharply their unanswered questions have come into focus. The basic outline is solid. Compact engines launch ultrarelativistic jets, prompt gamma rays come from dissipation inside the outflow, and afterglows arise from external shocks. The unresolved pieces sit inside that outline like high-pressure seams, where small differences in initial conditions can flip an event from a brilliant burst into near invisibility. One of the most fundamental unknowns is what the jet is actually made of. A jet can be baryonic, meaning most of its inertia is carried by ordinary matter, protons and neutrons, with electrons providing charge balance. It can be pair-dominated, composed largely of electrons and positrons. Or it can be magnetically dominated, where most of the energy resides in ordered electromagnetic fields rather than in particle motion. Each possibility leads to different acceleration behavior, different radiation efficiencies, and different spectral signatures. this is not a minor detail. Jet composition determines how easily Lorentz factors of hundreds can be reached, how severe the baryon loading problem becomes, and whether dissipation favours shocks or magnetic reconnection. Observations hint at both matter-dominated and magnetically dominated regimes, suggesting that the burst population may not be uniform. Some jets may begin magnetically dominated and later convert energy into particle motion, while others may remain kinetic from the outset. Closely tied to composition is where the prompt emission is produced. If gamma rays are generated too deep inside the jet, the region is optically thick and radiation thermalizes, erasing the non-thermal spectra that dominate most bursts. If emission occurs too far out, densities become low, and producing the observed luminosities requires extreme efficiencies. Photospheric models naturally generate a spectral peak at the right energies, but many bursts show broad, evolving spectra that demand additional dissipation above the photosphere. Synchrotron and inverse Compton models can reproduce this breadth, but they face persistent challenges related to spectral slopes, cooling times, and magnetic field evolution. The data are now precise enough that small assumptions matter. How quickly magnetic fields decay, how electrons are injected, how turbulent the flow becomes, and whether particle distributions are isotropic or anisotropic can all shift model predictions in ways that overlap with real observations. This makes it difficult to rule out entire classes of models even when tensions remain. Another unresolved issue is central engine longevity. The simplest picture once linked burst duration directly to engine lifetime. Long bursts implied long-lived engines. Short bursts implied brief ones. Reality is more complicated. Some short bursts show extended emission lasting tens to hundreds of seconds. Some long bursts display gaps and late pulses, suggesting intermittent engine activity rather than steady power. X-ray plateaus in afterglows indicate sustained energy injection long after the prompt phase ends. These behaviours point toward engines that can continue feeding energy into the outflow well beyond the initial explosion. That naturally raises the question of whether the remnant is always a black hole. This leads to one of the central open questions: magnetars versus black holes. In collapsars, black hole formation plus accretion is the canonical engine. In mergers, the outcome depends on masses and nuclear physics. The remnant may be a black hole almost immediately, or a hypermassive neutron star that collapses later, or even a long-lived massive neutron star, a rapidly spinning, highly magnetized neutron star. A magnetar contains an enormous reservoir of rotational energy that can be tapped electromagnetically over longer timescales. Such an engine can naturally explain plateaus, extended emission, and smooth late-time energy injection. Black hole engines, by contrast, provide a natural explanation for the highest jet powers and the cleanest ultrarelativistic flows, because accretion disks threaded by strong magnetic flux can extract energy efficiently. Observationally, both engine types may exist within the burst population, and the same observed class may not correspond to a single underlying remnant. Another major uncertainty concerns jet structure. Early models treated jets as uniform cones with sharp edges. Growing evidence favours structured jets, where energy and Lorentz factor vary smoothly with angle. In such models, viewing angle becomes a continuous parameter rather than a binary on-axis or off-axis distinction. This affects inferred energies, burst rates, and the interpretation of weak or delayed gamma-ray signals, especially in merger-associated events. Structured jets also provide a natural explanation for why some nearby mergers produce faint gamma-ray flashes while others do not, and why late-time radio emission can rise as the jet decelerates and spreads. Understanding jet structure is therefore essential for linking observed bursts to the true underlying event population. Beyond the main short to long classification lie populations that resist easy categorization. Ultra-long bursts, lasting thousands of seconds, challenge standard collapsar timescales. Their durations suggest either engines that remain active far longer than usual, or progenitors with exceptionally extended envelopes that jets must traverse for long periods. Proposed explanations include very large stars, unusual disk evolution, or entirely different types of central engines. Each possibility places severe constraints on baryon loading and jet stability over long time scales. Equally important, though less obvious, are failed jets. Not every engine that launches a jet produces an observable gamma-ray burst. In collapses, a jet may stall inside the star, depositing its energy internally and producing a supernova without a classical burst. In mergers, baryon-rich ejecta can choke a jet before it accelerates fully. These failed events matter because they determine how representative observed bursts really are. The bursts we see may be only the most successful, best-aligned examples of a much larger population of engines. There are also unresolved questions at the level of particle acceleration and microphysics. Relativistic collisionless shocks behave differently from the shocks familiar in non-relativistic plasmas. The fraction of energy given to electrons, the strength and coherence of magnetic fields, and the resulting radiation spectra are not fixed by first principles. Magnetic reconnection in highly magnetized relativistic flows is similarly complex, with rates and particle spectra that depend sensitively on plasma composition and field geometry. These microphysical uncertainties propagate upward into global burst models. Even the role of neutrinos remains unsettled. Accretion disks in collapsars and mergers are intense neutrino sources, and neutrino-antineutrino annihilation can deposit energy above the poles of the system. Whether this mechanism is dominant or merely auxiliary compared to magnetic energy extraction depends on disk properties that are difficult to observe directly. The multi-messenger era has clarified some questions while sharpening others. Joint gravitational wave and gamma-ray detections confirm merger origins in specific cases, but they also reveal a diversity of outcomes. Prompt black hole formation versus delayed collapse, strong versus weak jets, and varying balances between jet energy and ejecta. Each new event adds constraints, but also expands the parameter space that theory must cover. Progress now depends as much on observation as on ideas. The most decisive advances will come from faster and more precise localization, broader spectral coverage during the prompt phase, improved time-resolved spectroscopy, and reliable polarization measurements. These capabilities directly target the open questions of jet composition, radiation mechanism, and engine identity. Large samples of well-observed off-axis events, especially those associated with independent spacetime signals, will allow jet structure to be mapped statistically rather than inferred from rare exceptional cases. The brightest unknowns in gamma-ray burst physics are therefore not gaps in evidence, but points where multiple physical explanations remain viable within known laws. Each explanation works in some regime. Distinguishing between them requires observations that isolate cause rather than coincidence. Gamma-ray bursts already stand among the most powerful laboratories for studying relativistic outflows, strong gravity, and extreme plasma physics. Their remaining mysteries cluster exactly where nature is doing several difficult things at once: accelerating matter to near light speed, keeping the flow clean of excess mass, radiating efficiently without trapping photons, and sustaining or shutting down engines on millisecond timescales inside violently changing environments. The bursts themselves are fleeting. The questions they raise are not. And as detection improves, those questions are no longer retreating. They are coming into sharper focus, waiting for the next flash to decide between them.